All right, everybody. Today we're going to look at something called order of magnitude when we're looking at limits as we approach infinity. Infinity does have quite a bit of magnitude. So in the calculator, I'm going to graph e to the x, x squared, and natural log of x. And let's see, there we go. This is our e to the x, gets big real fast. Our polynomial function, x squared. I'm looking over here at the right-hand side, grows a little bit slower. And then, of course, natural log is a very slow grower. It does definitely approach infinity, but it's just getting there a little slower than the polynomial or the exponential function. So if we look at here at any of these points, we can see that the blue values are higher than the red values here on the polynomial, which are bigger than our natural log values. And if we go out at infinity, this is definitely going to be bigger everywhere. That'll be our next fastest grower, and this one will still be our slowest grower as x's get bigger and bigger. So, and that is actually true that all log functions, log and natural log functions, are slow growers. And then the next are the polynomial functions. And that's your, your x squared, x to the third, so on and so forth. And then our exponential functions are our fastest growers. And I'm abbreviating here for room. But our exponential functions are our fastest growers. And that's like e to the x, 2 to the x, et cetera, right? Those are our fastest growers. As a matter of fact, if I go in here and I change this out for a 2, and let's graph this again. There's our 2 to the x function. Doesn't look a whole lot different than e to the x. A little less steep because 2 is less than e. There we go. And if you look here, I'm going to ignore this natural log function, but if you look here before we get way out on big X's, if you look here, you'll see for a brief period of time, this red function is bigger. Those values seem to be growing faster, but then eventually the exponential function takes it over. And that's why in the middle, we're seeing some little bit of crisscross in here, but overall out at infinity, the exponential functions will always eventually overtake those polynomial functions. So I'm going to get rid of this, and let's just see how we can use this to help us evaluate limits when we have places of great magnitude, right? All right, so let's see. Well, we've done these before, right? And we've been doing this for a long time, this idea of order of magnitude with the horizontal asymptotes, right? Look, we're limits at infinity. This denominator is a higher power, has more magnitude than the numerator, and so we say that, and you could use L'Hopital, but we're going to go with the horizontal asymptote method and say that that's a slow grower over a faster grower, that this is going to 0. And at the same point, you can think of that with actual numbers if you want, if we're kind of going up by numerators are increasing by 1, but denominators are increasing by multiples of 10. You can see, lost count of my zeros, you can see that this number is just they're getting bigger and bigger and bigger, right? And you can flip those all and prove this point that if the numerator is growing faster than the denominator, it's growing by multiples of 10, and the denominator is only growing by multiples of 1, that these numbers are indeed getting bigger and bigger and bigger. And that's why we say when the numerator has a higher power, more magnitude than the denominator, that this limit does not exist. It's going to infinity. And then down here, where the powers are roughly the same, we say we just make a fraction out of those coefficients, 2 over 1, and we would get that this limit is 2. And you can see the highest powers, this is always twice that one. So, that's kind of like saying if this is a 10, this is a 20. If this is a 20, this is a 40. If this is a 40 or 30, this is a 60. And, you can kind of see those all are going to reduce to 2. Okay, but what this idea of order of magnitude does, including these functions, is kind of cool. We can even throw in other functions if you want. Let me get to my graph here, and we can throw in the sine function. And I think we all know that the sine function has very little magnitude. See, look, it's real little right there. It's only between -1 and 1. Same with cosine. So it's an even slower grower if we're looking at magnitude. It's not really growing. It's just ping-ponging back and forth between two values. It's even has less magnitude than the natural log does. So we can use this idea when we're talking about way out at infinity for a lot of different functions. So let's go ahead and look at this one. We know from what we just took notes on that exponential functions grow faster than polynomials. So this bottom has more magnitude than the top. So we're really looking at something very similar where the denominator has more magnitude than the numerator. And we will indeed be going to 0. It's that easy. I want you to think about what happens if you have to use L'Hopital for this one. You're going to derivative e to the x will keep being e to the x, and the derivative of this will keep dropping down a power. But you'd have to do it quite a few times to actually get to the result of that being 0. And then this one, once again, this has more magnitude. Put them in your calculator, but you'll see that this exponential will eventually take over that power function, even though it's a super high power. And so we are going to say that the numerator has more magnitude than the denominator. So we're right back up here. Put it in your calculator and look out at infinity. Eventually that will look like it's going to increase without bound. And then this one, we've got natural log is a very slow grower. Polynomials are a little faster, so the denominator has more magnitude than the numerator, and we're going to be looking at going to 0 again. And this one, the line y equals x is a faster grower than root x, right? We can kind of see that. I guess they should have hit right there, but I'll make that dot real big. And so we can see that this should have more magnitude, so we should be going to 0 again. Or you could have simplified it, x to the 1/2, so that would be 1 over x to the 1/2, and 1 over infinity is going to 0. Or you could have used L'Hopital here. There's so many different ways now that we can do this, but I hope you're understanding that order of magnitude is a pretty quick and easy way to do this if it works for us. Okay, so that means by work for us, I mean we're looking out at infinity. Okay, let's try a couple here. You can pause me and give it a shot and see what we're going for here. Limit as we approach infinity. This is the highest powered term, has more magnitude than the natural log because it's a polynomial. So the numerator has a higher magnitude than the denominator does. So we will say this is going to have no limit. And then we can go ahead and look at this one. The sign is really negligible. This is the term with the higher power, and this is the term with the highest power. And because they're the same, we're going to make a fraction out of the coefficients. Please put this equation in your calculator. Look way out at infinity. You'll see that there's a horizontal asymptote there. Okay, try that last one on your own. See what you get. Okay, if you got 1/5, you made a rookie mistake, right? This is not a limit as we approach infinity. This is a limit as we approach 0. So we can't look for a horizontal asymptote or use that idea of the highest power. What we're actually going to do is what we always do first, is we should try direct substitution. We do have some quick shortcuts if it's a limit at infinity, right? But when it's not, we have to try direct substitution first. So 0, 0, 0, 1 over 0, 0, 2, and our limit is 1/2. So please, 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 order magnitude is wonderful. Make sure you've got kind of listed the notes here of what grows faster than what. And remember, we can only use that if we're looking at places with great magnitude. All right, folks, that's it.